force between two parallel currents, and from here we can define 1 ampere of current, and that is called the international ampere. The SI unit of current is ampere, and it is defined from here. Now we have learned that there exists a magnetic field around a current carrying conductor. Yes, if there is a conductor, then there will be magnetic field around the current carrying conductor. And also, a current carrying conductor experiences a force when it is placed in an external magnetic field. See here, if this is a current carrying conductor, then there is a magnetic field due to this current. Again, we have already discussed that if a current carrying conductor is placed in a magnetic field, then it will experience a force. Thus, it is logical to expect that two current carrying conductors placed near each other will exert force on each other. This is a conductor, a current flowing through this conductor, then there will be a magnetic field around this conductor. Now we place another current carrying conductor, then we can say this current carrying conductor is placed in a magnetic field produced by this current carrying conductor. So this current carrying conductor will experience a force. Let us consider two long or very long, rather very long straight parallel conductor 1 and 2. This is conductor 1 and this is conductor 2, right? Carrying currents I1 and I2 in the same direction. Clear? Here we consider two current carrying conductor carrying currents I1 and I2 in the same direction. One conductor named 1 and second conductor named 2. And they are separated by a distance. Let us say the distance is D. D is the distance between the two conductors, and they are placed in vacuum. In conductor 1, I1 current is flowing. Therefore, the magnetic field due to this current carrying conductor at a distance D will be B1 is equal to mu naught by 4 pi to I1 by D. That means at each and every point of the conductor 2, there is a magnetic field B1 which is mu naught by 4 pi to I1 by D, and it is perpendicularly into the bore. That means its direction is perpendicularly into the bore. We have discussed that. We have calculated the field due to a current carrying conductor both from Biresh and Ampere's theorem, from both, and its direction, since I1 is this, and at this position the if let us say this is R and this is an ideal cross R, this is clockwise, that is into the bore. Here this is the B1. Is it? Now if we say that, or if we consider a current element I2dl2, I2dl2 is the current element of the conductor 2, and which is is equal to F21 is equal to I2 dl2 cross B1. Is it or not? Already we have discussed or proved that a current element ideal placed in a magnetic field B experiences a force F is equal to ideal cross B. We have considered I2 dl2 current element of the conductor 2, and it is placed in the magnetic field produced by the conductor 1, which is B1. Therefore, force experienced by this current carrying conductor or element of this current carrying conductor I2 dl2 is equal to Ft1 is equal to I2 dl2 cross B1. Now see here, B1 is perpendicularly into the core and I2 dl2 is along this direction. Therefore, the force F21, magnitude of the force F21 is equal to I2 dl2 B1, and which is equal to I2 dl2 into B1 is this mu naught by 4 pi 2 I1 by d, that is mu naught by 4 pi 2 I1 I2 by d into dl2. This is the force experienced by I2 dl2 current element of the conductor 2 due to the I1 current or due to the conductor 1. And what is the direction? You can get the direction from this and from the left hand, Fleming's left hand rule also. See here, I2 dl2 is along this direction, B is along this direction. Then you have to rotate a corkscrew from I2 dl2 to B1. That is, it will rotate in this direction and the screw advances in this direction. Therefore, the force is along this direction. That is, this force is towards the conductor I1. Right? Similarly, since I2 current is flowing through the conductor 2, therefore, it will produce a magnetic field around the conductor, and magnetic field at each and every point of the conductor 1 is B2 is equal to mu naught by 4 pi 2 I2 by d, and it is out of the board. See here, current flowing in this direction. Therefore, the field at this position I2 dl2 cross R in this direction, that is B2 is perpendicularly out of the board. See here, this is I2 dl2 and in this time R is along this direction. Then rotate a corkscrew from I2 dl2 to R, ideal cross R, that is rotate anti-clockwise. Then it will come out of the board. That's why B2 is perpendicularly out of the board. This is B2. Now, we consider a current element I1 dl1. I1 dl1. Now, this current element is in the magnetic field B2 due to the conductor 2. Then it will experience a force, and that force is F12 is equal to I1 dl1 cross B2, and magnitude of this force is I1 dl1 B2 sin 90 degree, because I2 dl2 is along this direction and B2 is perpendicular out of the board. Therefore, these two are mutually perpendicular. Therefore, F2 is I1 dl1 into B2, and you can write I1 dl1 into B2 is this mu naught by 4 pi 2 I2 by d, and you will get mu naught by 4 pi 2 I1 I2 dl1 by d. And direction of this force is, this is I1 dl1 and this is B2. Then ideal cross B, ideal cross B. From From this side I will rotate clockwise, then screw will be advances in this direction, that is force towards the conductor 2. This force is towards the conductor 2. Now force on conductor 1 is towards conductor 2 and force on conductor 2 is towards conductor 1. That means these two are attracts each other. The conductors 1 and 2 attracts each other. And see here, from here, F is F21 by dl2 is equal to mu naught by 4 pi 2 I1 I2 by d, and here also F12 by dl1 is equal to mu naught by 4 pi 2 I1 I2 by d. Now F12 by dl1, that means force experienced by conductor 1 of unit length, force per unit length. That means the force per unit length of the conductor, is F is equal to what? F is the force per unit length of the conductor, which is equal mu naught by 4 pi 2 I1 I2 by d. That means you can write mu naught by 2 pi I1 I2 by d. This is the force per unit length of the conductor, and which is same. If the currents in the two conductors are in opposite direction, that means in conductor 1 current is flowing in this direction, but in conductor 2 current is flowing in this direction. Then what happens? Then see here, when current is in this direction, the force was in that direction. Now see here, since current flowing in this conductor is same, therefore magnetic field is into the board. Now current is flowing downward. Now rotate it. Ideal cross B, ideal cross B. Ideal in this direction, B in this direction. Now ideal cross B, rotating in this direction, clockwise. Then it will move in this direction. Therefore, in that case, force on conductor 2 will be along this direction, that is away from conductor 1. Similarly, you can find the force on conductor 1 due to the conductor 2 will also away from the conductor 2. That means if the current flowing in the opposite direction, then the two conductors repels each other. Thus we can say two long parallel conductors carrying currents in the same direction attracts each other, and current, if the currents are in opposite direction, they repel each other. If I1 is equal to I2 is equal to 1 ampere, D is equal to 1 meter, then F is equal to 4 pi into 10 to the power minus 7 by 2 pi into 1 divided by 1. That means you get 2 into 10 to the power minus 7 Newton per meter. Clear? Now reverse these things. That means if I1 is equal to I2 is equal to I, that means same amount of current flowing through the two conductors separated by a distance 1 meter experiences a force 2 into 10 to the power minus 7 Newton per meter, then we get 2 into 10 to the power minus 7 is equal to 4 pi into 10 to the power minus 7 by 2 pi into I divided by 1. From here you get I square is equal to 1. That means I is equal to 1. Is it clear? That means you can define from here I is equal to 1 ampere, you can define. What is the definition? If two very long straight parallel conductor separated by 1 meter in vacuum carries same amount of current experiences a force equal to 2 into 10 to the minus 7 Newton per meter, then the current in each conductor is 1 ampere. Two very long straight parallel conductor separated by a distance 1 meter in vacuum carries same amount of current. Then if the conductor experiences a force equal to 2 into 10 to the minus 7 Newton per meter, then current flowing through each conductor is called 1 ampere.